Hello everyone, my name is Artur Kuzin. I'm working on the X5 retail groups, and today I'll talk about my experience related to a competition that's held on Driven Data platform, and it was about the classification of the animals in the savanna of Africa. So the task itself looks like this. The host of the competition places some cameras somewhere in the savanna, and these cameras takes series of the images with some period. So the amount of images in one series is arbitrary, but not large. It's about 2 to maybe 5 images per sequence. So for participants, it suggests to develop some solution that perform classification to output the probability of every class that appear on the image. So it was about 70 classes of the animals, and one of the class was empty. And actually it was huge imbalance in classes, and the class empty was the large one. The metric was log loss. So as you can see, it's very straightforward and very actually not some tricky competition. And my solution, to be honest, was quite boring. So I decided to share with you my experience with training ImageNet from scratch. I think it's very important because, for example, if you take default model like ResNet 50 from Torch Vision, then you'll get top 1 accuracy about 76%. But if you will implement some tricks and using this two article, you're able to achieve about 3% more high accuracy for top 1 accuracy for same network with some minor tricks. So I spent about 2 months, implemented all these features in my framework, so I would like to share my knowledge that I get from this experience. The first one is about tweaks of the network. So well, actually it's a lot of tiny modification of ResNet, of vanilla ResNet. So on the left side of the slide, it's vanilla realization. On the right side of the slide, it's ResNet D modification. So there are 3 modifications that's highlighted with colors. The first one is about first conf layer. So in vanilla realization, it's one conf layer with kernel size 7 by 7 and try to. Instead of this, in D modification, it's used 3 layers of conf with kernel size 3 by 3, and the first layer is try 2. So apparently, the receptor field of this 3 conf layer the same as for the first layer 7 by 7, but it's well, more layers, more depth, and more non-linearity for these 3 layers. The second 2 modification is about bottleneck layer, bottleneck block. So it's about putting some average pooling on the skip connection branch, and to move straight from the first conf layer 1 by 1 to the second layer 3 by 3. It's important to know that these tweaks boost some kind of overhead, and this network become about 10% more slower than vanilla realization. But it's at the same time it's become more accurate, about 0.5% for the same kind of training procedure. The next one is scheduling. So default scheduling from scratch training is step decay. Instead of this, the author suggests to use warm-up with cosine decay. The warm-up is increasing learning rate from 0 to the target initial learning rate value during some epoch. And then it's will appear cosine decay instead of step decay. So on the left side of the slide, it's learning rate versus the epoch, and on the bottom it's validation accuracy. But if you will implement these features, you can think about how often you need to update learning rate, because if you use warm-up, it might be not obvious how to update learning rate, because you can update learning rate 1 per epoch or maybe 1 time per every step. Actually, I tried both, and it looks like it's the same. So you can not think about how to implement this warm-up. You just take the default PyTorch scheduling and just update it a little bit. Also, one little feature that I also implement, it's some kind of cooldown the epoch. So as you can see on the right side of the slides, it's about 10 epoch at the end with the minimum learning rate. It's because it's often that you achieve the most accurate checkpoint on the very end of the training. So you also always think that if you wait a little bit longer, that it will be more accurate. So I tried just a little bit more epoch to not think about this. So I just take the best epoch from the whole procedure without any frustration. The next thing is about label smoothing. So on the default realization, you just have one hot vector of the target. Instead of this, it suggests to decrease the true value 1 label with some kind of epsilon, and to increase the rest of the label with epsilon divided by amount of classes minus 1. The epsilon is typically 0.1, but once again, if you look carefully to the realization of a label smoothing inside some kind of reference repository, then you find that no one modified the target. Instead of this, all developer just modified the loss. So you can find the correct loss in repository of NVIDIA. The next thing, it's about mix-up and cut mix. The mix-up is kind of a pixel-wise mixture of 2 images. So if, for example, you have image of the dog and the cat, and you mix them on the pixel level, so you achieve some kind of cat with just of the dog on the background. Also, it's a cut mix when you just copy-paste some crop from one image to another. But it's actually, I spent quite a lot of time using mix-up in different competition, and I also struggling to achieve better performance than without them. And on the second article that I highlighted on the beginning, it's said that there are 2 kinds of mix-up realization. The first one is just mixing the images inside one batches with itself, because, well, it's more computation efficiency. You just generate one batches, shuffling the indexes of these batches, and mix up it with itself. The true realization just get 2 independent batches. It's 2 times more computational and efficient on the CPU, but it's allow you to achieve better performance in terms of accuracy, because you have 2 independent batches. So all of the time I use type 2, and I was struggling to achieve better top 1 accuracy. And this approach also applicable to cut mix. So if you going to choose to use cut mix, then I believe you should mix this with 2 independent batches. So I implement all these features inside my framework. I'm actually switched to PyTorch Lightning. It's kind of a library like Catalyst or maybe Ignite that allow you to develop your own pipeline, not on the Torch, but it's kind of a higher level wrapper around the PyTorch. So it's allow you to get NVIDIA Apex from out of box. So I always use Apex with one optimization. Also, I implement DALI data loader in the same way as the default Torch data loader. Also, to make more fast experiments, I implement some kind of progressive input size increasing, I believe. So it looks like you start in training with very smart, small input size, for example, 128, and then increasing the input of your network then you saturated your accuracy. One more thing about the DALI, NVIDIA DALI, it's also very important. So it's NVIDIA library that allow you to make JPEG decompression inside GPU. It's very important because in this case you have no bottleneck on the CPU. You now utilize your GPUs more efficient. But it's also very important to know that it produces not exactly bitwise output of JPEG decompression comparison to the other framework like OpenCV. So if you train your network on the DALI and then try to compare the score you get on validation with, for example, PyTorch data loader, then you always get some minor accuracy drop for about 0.1%. But for fast iteration and the fast training procedure, it's very important because if you train some kind of lightweight network, or maybe you doing distillation, then it's very important to use DALI because you have no bottleneck on the CPU. So using all of these features, I was able to achieve 78.8 accuracy, and it's how it looks like. So it's 4 stages. You can see the learning rate decay on the average stages and the accuracy, how it's changed from stage to stage. And using the very same config file for the training, I was able to get 5th place in the Driven Data competition on my first attempt. So basically I just changed the path from ImageNet to the dataset of Driven Data. It's more funny because I even didn't change the loss and the target, because on the Driven Data it's multi-class, multi-label task, but on the ImageNet it's only classification, so you have one label for each classes. So I was very happy and decided to dive into this competition using all of my knowledge from the ImageNet. So a couple of words about the data size. Actually, it was quite large, not crazy large, but something in the middle between the full ImageNet and ImageNet 1K. And for the public leaderboard, it was very small amount of data. So I do believe that my first attempt was kind of random, because the little amount of data and a lot of noise. So it's also very important that the dataset was split to some kind of seasons. So seasons is like, or maybe session, it's like one period during of which was collected some kind of data. So public leaderboard was based on season 10, and I decided to take the whole 10 season as validation set. And the private leaderboard was calculated on the dataset on the season that didn't available public. So it's completely closed part of the data that no one of the participants can get or can see. And its size was comparable to one season. So I have validation that's very close to the private leaderboard validation part. The raw dataset was about 4 terabytes, so it was kind of pain to download this whole dataset. But Pavel Pleskov downloaded all of this data and reduced the size to about 0.5 terabytes using just compression the size. So it's not necessary to train on the whole image because, well, it's very large, and the 500 pixel on the large size, it's quite enough to train the model. So Pavel was, after this, I believe, dataset expert on the Kaggle, but then it was banned, and it's a very sad story. So the only thing that I changed, and it was very important, in particular in this competition, it's a preprocessing step. So for the best model, I just take, for training procedure, I take Pavel images that he reduced to 500 pixels to the long size, reduce the size to 850 pixels, and then make random crop to the training procedure. So for the validation part, I make similar step, but without random crop. So basically, I training on the more small size images than for validation parts, but the scale was the same because, well, I believe the scale is very important to make no discrepancy between train, validation, and test parts. But for the test part, it was crucial to make the same step that Pavel was for reduction of the size of the data set. So it was kind of crazy pipeline. I take raw images and reduce the size using image anti-aliasing interpolation. Then I take my parts and reduce the size using image one-cross interpolation to the size of the validation parts. So yes, if you didn't do this every steps, your loss significantly increased because, I don't know, the bitwise output of the images and the artifact was different. And for test, I didn't use some kind of 5 crop or 10 crop validation test time augmentation. I just use mirror augmentation. So my final solution looks like this. The bolded part that I did change for this competition. So I basically take different models because I do believe that Facebook ResNext models that they did train on the 1 billion images, it's very good. So it's have very I don't know, representative feature that allow you to increase your model accuracy despite of the modification of the network. So the data is very important, and the large pre-train on the large data is very important. Also, I make the fine-tuning, so I reduce initial learning rates, I change the loss and the metrics, and I didn't try to different metrics, for example, focal loss or so on, because the target and the metrics was the same, and it's no necessary to, well, play with these parts. And also I slightly differ the progressive input size and all of the averaging. For example, inside one series or inside the TTA, I just use geometrical mean. And I take, well, I finished second, I believe, because it's not finalized leaderboard, so I don't use exactly what my score, but I achieve, well, I receive email from the host of the competition, and he said that I will take second. Another solution that I find in the ODS Slack was from Ivan Bragin. So he used Keras. The best model was Inception ResNet version 2, and he did use he used second level model. It's like GBM, because he do believe that it's important to find the empty images, because it's a lot of empty images, and it's highly affects to the final score and final metrics. He also used mirror TTA for test time augmentation, and he used batch, not large batch, because he used not large GPU memory. And this is the final slide. So I try to find the images that have more metric or more error rate. So it's samples with the most larger loss value. So as you can see, it's, well, kind of strange, because a lot of images have just artifacts. And it's kind of strange images like zebra at night. I believe it's very rare situation, so network can't learn this from data. Well, also it's elephant on night. So that's all. Thank you for your attention, and I will be pleased to answer questions.
Thanks, Artur. If you have any question, please ask in English or Russian.
Thank you, Artur. Please, you said that we used progressive input size, yeah? So I've seen this earlier. Does it matter that we used progressive size, or can we use decreasive size?
I believe it's not make sense because the larger your input size, the more accurate your model become. So it's important to make the most accurate setup on the end of the training.
Oh. Well, but can we use much bigger size and then decrease to the target size?
Do you mean it's for purpose for decreasing the model computation?
Yeah.
I think it's more easier to use just distillation. So you just train the large model and then distill the knowledge to the more small model. It's much more efficient than just training on the large size because it's very long procedure.
Well, it's computation.
Yeah, computation.
Okay, thank you.
Other questions? So I also.
From this slide, can I confirm that the database didn't have enough images of empty land and night images? And that's why they had the most error?
I believe there are not large amount of images with artifacts, and because well, it's quite not large, but if you look carefully, then you find that, for example, on this slide, it's kind of central rectangular artifacts, and it's not about enough night images. It's about rare cases. Then zebra walk at night on savanna, I believe. I'm not expert, but it's my hypothesis.
What about all like the empty land images where there are no animals?
I don't know.
Other questions? You had only one attempt to submit. How did you choose the final solution? What averaging, use simple averaging or Gmin, as you said?
Well, I have actually 5 attempts, so I try some kind of approaches. The geometric mean, it's from my past experience, it's more accurate than just mean averaging because, well, you have probability distribution. It's more mathematical correct to make geometric mean instead of just mean. Yes, well.
Thanks, Artur, again.